name is Mark Gamble. I'm an inventor from Lansing, Michigan, U.S. Sometimes I call myself General Gamble. That was back when I was trying to help the Fukushima situation. This presentation is on floating wind farms. Only 10 years ago, floating wind farms were sort of considered a whimsical idea for energy production. It took the dark days of Fukushima to realize what their true implications were. Now it's one of the primary hopes for the future. One thing standing in the way of the cost of infrastructure, of the project, is the cost of infrastructure. And yet, I still think that the best solutions for floating wind farms haven't been tried. Many different designs have been created. Most are still theoretical. And what is clear is the advantage of being at sea further outweighs the costs of building. And now we only have to figure out a way of making the total infrastructure costs cheaper.
That efficient.
If the wave of designs made out of oil platforms teaches us anything, it's that we have to look for new solutions in the future, because the solutions in the past weren't specifically made for the use of a wind farm. What we see in front of you is my second attempt at a best design for my ideas in a floating wind farm. I would like to explain that I'm always working out something better, and when I feel that enough changes have been made to make a more optimal design, then I update the design. The most important thing about this design is that it consists of floating platforms and rafts that make up and connect together to make a superstructure. It's that concept and the cost savings around the concept of the superstructure that this video is made around. The moving theme of this first attempt was to create a tessellated pattern that, when hooked together into a block formation, would create a huge superstructure of non-colliding towers. Since these towers are mechanically connected, there's really no way for them to collide. The design, I thought, was inefficient, but it was useful for showing the process of how something like this could be accomplished using the tools and transportation methods that we have on hand. One benefit is that a plastic and metal raft can be put together on the water before you put it together on a production line, meaning that you could sink the metal towers into the raft before finishing the assembly. The very nature of a raft is to avoid capsizing, and being partially submerged helps stabilize the whole structure. But this type of stability might not be that necessary if the connections to the superstructure in the individual raft formation make the movement or freedom of motion of the towers very limited. If you use an upper and a lower connection, then I think you could achieve this. Greatly upscaling can become an issue, as is well known, in unstable weather. Once the weight of the surrounding rafts is accounted for, though, I think it can lend a certain level of stability because of the huge amount of inertia. Ferries capsize, aircraft carriers don't. This is all a matter of weight distribution and over a distance, and inertia and frequency from incoming waves versus the inertia of the superstructure. This is sort of a graphic representation of my thoughts on the system versus that of the best floating design that I've seen yet. You could easily put these floating spars together in the same way and proceed. And in fact, I think that there are probably better ways than the current towers that we use. But I'm not here to sell a cat at a dog show. For Regardless of the ultimate type of floating platform used, mechanically connecting these towers together on the raft level and then the superstructure level is meant to provide extra stability and savings over the current method. Connecting these rafts mechanically can achieve a great cost savings in the transmission cost. Underwater cables for connecting the towers to the transformers are in the rafts. So, connecting the towers to the transformers in the trunk is many times less. And you can protect the cables from seawater. My understanding of traditional seafloor embedded anchor systems is that such an existing anchor system is probably substantial enough to hold a vast network of rafts in place, saving on the anchoring costs. It will take cranes, self-sinking pillar anchors, trains, chains, and technicians. A lot of seawater and airspace will be used. Together we'll create a vast and secret place, lighting the world with spider tracers. A place where seawater and where seagulls and sea-legged men meet. With it all, we'll bake our bread. The next part of this presentation is on how the economy of scale for this system would work, and it covers efficiencies and core ideas. My vision for this is a world where utilities are built for an open market, and where old models are sold and refurbished traded just like used cars, where places like Haiti and New Zealand can afford an old set of equipment. In order to make something so cheap and ubiquitous, its materials must be cheap and easy to find. All the materials here float to balance out the added weight of the towers. Such materials can be better suited for ocean chemistry. You would need a high amount of materials. The amount of materials can be offset by the ballasts and other air spaces. And most of the components here are meant to be modular. And they must be modular in order to tessellate and connect to the rest of the superstructure. It's made so that a single raft can be disconnected, replaced, and pulled back for repairs. Some of the materials that I mentioned can be obtained for free, or you can pay or be paid to remove them, such as waste wood from disaster sites and polystyrene, which is already too abundant. I wanted to solidly detail an expense outline, but I had no luck in finding an expense report for things like monopoles. On this matter, instead, I put together a cost reference from various websites that I found that could sell recycled steel products and recycled polystyrene. The one issue is that the cost of copper and steel have gone up recently, and luckily this design uses less of those types of things than the old floater towers, or designs like the Freewind. Here are some important material properties ahead of time to explain why it should float. Condensed polystyrene is closer to about 20 kilograms per cubic meter. This is taken into account later, and the buoyancy analysis of this full structure would require an AutoCAD model. The real question is then how you'd make such an enmeshment of steel and plastic float together. This is an idea, with the idea in mind that you never let the steel come into contact with the seawater. Instead, the whole raft is covered with a resistant plastic to reinforce it, and a wooden shell with layers of polystyrene, or the layer of polystyrene foam between the wood and the hard plastic. Only the inner frame is made of steel, and this supports the plastic ballasts and couplings from the wind tower and monopoles. Great pains are going to have to be taken to distribute the weight of the ballasts, or the weight of the towers and the inner frame with the weight of the ballasts. And I have ideas on how to do this, but I'm not going to cover them in this article. It's going to take quite a while.
side views.
The square
Yeah,
design is useful, and it can be
now,
tessellated
the
and
thing to
make
know
a solid unbreakable chain. However, it
is
creates a solid wall.
that if
This presents a
the
problem to
input
almost
has
any wind
something
farm
missing that
generally.
may be flawed, I don't
One
know what
option
it
would
is,
be to stagger the height
is
of the
that
turbines.
if
This
you
is still
take
suboptimal. The triangular
and
design can
hook
still
enough
be
of these
non-colliding
things together,
and tessellated.
basically,
All of the
you
tower
tessellate it in a
connection,
way
or the
that it
type
would
of
never
tower connection that you
collide,
use, or raft connection, is really what you need to know
at least in
to
this
make
picture.
the offset of these towers
And
respected to the
basically
wall
it'd need like
not so
way
much a
more
factor.
because it'd be
But
a
this
mix
isn't
of
something
all of these,
I really am covering in this, although it's easy to figure out, and I've thought about it quite deeply. This is cited in almost all of the articles I've read, and it's that the economy of scale is one of the largest factors in building a wind farm operation and its success. The larger the wind power farm, the higher the output, the faster the plant makes back its principal. The main reason that you don't build a large-scale wind farm is they're not made, or that it takes a lot of money to make these very large pieces transportable when they're oversized. And also, there's an inherent stability in putting a wind tower with most of its mass being on top, 180 meters in the air. One of the real constraints of this is the materials. And though I've found no estimation made, I think with a reasonable, though I've found no estimation made, I think a reasonable model might be workable. And this is the closest I've come to it, is the white paper of Mr. Johannes George. Thank you very much, Mr. George. As you see, this design has similarities to my own, but the paper lacks an expense report for things like buoys and nacelle towers. What it does include is a detailed report of the weights of monopoles, nacelles, and blades in the theoretical 10 milliwatt range. The density of steel is about 6.5 times that of polystyrene minus the density of seawater. Meaning that if you take about 6.5 times the amount of polystyrene, you can float the same, or that amount of steel in seawater. So, as a triangle, in order to make 3 such towers float, it would take roughly 90 meters by 90 meters by 7 meters tall of polystyrene. Most of these material prices can hopefully be reduced and made less using methods to assemble this giant craft without the need for shipping huge parts, and with the use of very large ballasts to offset the weight. In this model, wood, polystyrene, and PVC from an outer shell are used to hold in the contents and to protect the steel superstructure from seawater. A lot of these materials won't be needed, as ballasts would take up the majority of the weight. This also means that the design allows for an error in the exact weight of the whole raft by using the ballasts as a control on the diving mechanism. Most of this can be changed around, and I wish I had the time to make an AutoCAD model, but I don't have one at this moment. The scale of this model is not determined or conveyed in this pictograms, though I do realize how important it is. However, many of the important challenges and issues of scale are summarized here. Most recent idea, however, could be built in smaller chunks than the 90 by 90 meters. The better weight distribution and wider fan array are also pros. There are also many other changes I would like to make before investing the time in making an AutoCAD model. The added weight of using cheaper I-beams for construction in the raft structure could make the overall job cheaper as well. All the parts, except for the blades and monopoles, could be moved by train. It would make it even more cost-efficient to construct the towers out of I-beams, and simply counterfloat it with things like polystyrene. Anyway, this is done. The price point is key. The price point, according to this article, is close to 1 megawatt for 3 million euros. Until presently, this has been a much larger problem, but the high wind model is a quantum leap in the direction of price point stability. And hopefully, this will be a similar jump forward. It's true right now that all of our designs that we hold today are backwards anachronisms. The tailor used to only have the knife and the needle, and then new looms and scissors were invented. Now they have the sewing machine. My designs are not what they should be, nor is anyone's. Like computers or solar power, how efficient the design becomes is a function of man-hours versus what we are trying to do. ENIAC in the turning machine did not yet have the transistors, and it would take years before we could put these pieces together. With each new innovation and design, we are not going forward or backward, but advancing an art form. So there are many things people have made, extra features and efficiencies, that if communication stays in the same spirit and level of innovation, it follows that all of our designs will become old and suboptimum. Scissors were supposedly invented by Leonardo da Vinci, but the first scissors were less efficient. Put these efficiencies together, and you come up with a beautiful Frankenstein monster, free to romp upon the sea lanes, and play and dance. Well, my name is Mark Gamble, and I hope that this presentation has brought some new ideas to you. You can reach me at the number on this card. Thank you very much for your time, and I hope you have a great day. Let me lead you out with the end of Man Who Sold the World by Nirvana Unplugged.